Hi everyone, and today we'll make a data science data analysis on this diabetes data set. We'll try to predict if someone have diabetes or not. So I have this data set downloaded, and I also have this make.json file which I took from this fast benchmark telegram bot. If I push start and if I ready, I can get this one. So that will help me to make the structure of diabetes C3 and get the report with prediction. So here is fastbenchmark.me, here are the instructions, so here is the link to the bot, you can use it, no problem. Okay, so let's say we want to Python make JSON file. So we want to predict outcome out of diabetes C3. Okay. Oops, sorry. Diabetes, sorry. Okay. So we should have the structure. Okay, so that's how it looks like. So the columns, metric, and its data types. This one we will send to bot, and we got the prediction here. Let's start Jupyter Lab. Okay, and look at our prediction. Start. So here we will read the data, we will deal with wrong CSV format here if it is wrong. For example, if we have unnamed columns, that is the wrong format. Okay, so here is how our data looks like. Here is the pair plot, so we can see the connections between these data. So these zeros, I think that's sort of NA. Okay. So let's look at the prediction, because fast benchmark will make a prediction very fast. So here we have this prediction on the splitted training set. We have splitted it while reading data, and here we split it again because we will use it to generate new features, test it, to tune our model, and so on. So let's look at the feature important. The diabetes pedigree function, BMI, and so on are very important. So let's just copy this. So here is the prediction on the splitted set. Let's look at the prediction on our real test, which we splitted on the top here. So this first split made us a real test actually. So let's look how it fitted to real test, and the score is better. So while we have so small amount of data, the scores on different subsets would be very different. As you see here, we have 0.85 and here 0.75. So the main thing that fast benchmarking is doing for you, it make this model very fast. So you can see if you can predict something using this data or you cannot. So here we can see that we can predict something and we can do it pretty good. So let's work with that data. Here you have the error statistics, so it will just find the main errors you have and the largest errors you have, and will show how the data of the same cluster, I mean the same no, the mostly the same values of each variable, which are sorted from the most important to less important. So we have these errors, and this is our training. So if they are pretty same, that means you can't actually make the prediction better. If they are more or less different, you can improve it. So as we can see here, this diabetes function here and here are pretty different actually. Their average is the same, but the values itself are very different. So maybe we can improve it. Not much, but maybe we can improve it. And again, this is the fit to real test. The score is 0.855, and after all of this we will fit it again. So now, as we did not make any model tuning, categories tuning, feature engineering, we have exactly the same score here. So after we will make all of these tunings and engineering, we will look at this score, and if it will be better, if it is better, we improved the model. If not, we did not improve the model. So let's try to improve our model. First, what we need to do is to generate some new features here. So let's look at the data. Maybe we'll understand which features and how to generate. Okay, so here is our target. It's 400 zeros to and 2.500 ones. Pretty balanced actually. So we don't have a super rare categories here, so that's good. Now let's look at these pregnancies variable. So mostly 0. Okay, what we have else? We have glucose, pretty much. We have blood pressure. We have skin thickness. We have insulin and BMI. The BMI is body mass index. It's your mass divided by your height. Actually, I can call it length. So as I am 1.8 meters and I weigh around 70 kilos, so my BMI would be 1.8 squared. It would be something like 3.24, and 70 divided by 3.24, it will be around 22, I think. Yeah, so my BMI is 22, so it's somewhere here. Okay, So what else we got with diabetics pedigree function here, and age. We got age. So as we see, there is not so much people who are older than 60, so maybe for them we will not get good prediction, but for those guys, I say from 20 to 40 it would be pretty good. Okay, so let's go to feature generation, and let's copy and paste all of those columns again. And our feature generation section is here. Let's just add the markdown line with all those features, and let's generate some new features here. So let's say like this. If you want variable 1 times variable 2, just use it like this. So what we want to do here is to, for example, make the variable called BMI times age, which is, I think that large BMI on if you are not old man, it's not a problem actually, but if you are old, large BMI could be a problem. So I will just make this variable BMI times age, which will be data BMI times data age. Okay, so next what we can do, let's look at this diabetes pedigree function. I don't know how to use it, but I think it should have some connections with BMI and age, and I will just test it. So I will say times. So I will say that I want to make 4 variables based on this. So this times age equals 2, equals to data of this variable times data age, and the same I will do. I'll call this per year, so I will divide it by age, so it's per year. Okay, and what else? The same for BMI. So BMI, and we'll there here, and here. Okay, so what else we can do is I think glucose may be for a large BMI. Large glucose is not a problem, and for small BMI it will be a problem. So let's do glucose per BMI, data glucose per BMI. It's equals to data glucose divided by data BMI. Okay. What else? Maybe we should make it the same for year, for age. Okay, pair year, age. Okay, and these pregnancies, I think it should also be divided by age, because a lot of pregnancies when you are, for example, young, when you are young, it's strange, and if you are, for example, 40, it's maybe better for your for you for your health, or not, or maybe not. We will just check it. Okay, let's check if data pregnancies per year equals to data pregnancies divided by data age. Okay, so now we can restart all of this. It will use our new variables, and we will just say that we want to tune categories. Actually, that would not work because we don't have any categories here or the numeric, but let's just try, and we will tune the model. I think this will be helpful. Okay, so now let's restart it all. So here are our variables, very easy to generate. You don't need to generate it to training set, to test set, again this copy pass and so on. Not just data, no problem. Okay, so here is the initial score for category tuner. This is the score on 5 cross validations. So it's you see here, it's the average score on 5 cross validations. Let's look at the score for model tuner. So it's now try different methods. Let's try exact, prox, and hist, and you see the initial score is like this, and the score for you see here for approx method is a bit better, so we will use that method. And let's look, so for different subsamples, let's look which is better. So the subsample of, you see here, 0.5, we have the best score actually. And now let's look at the depth. So we have max depth equals 1 will give us the best score, and this is, I think, the local optimum here for max depth, but we'll check others. Maybe somewhere here we will get another optimum, but it looks like we will not. Okay, so we have now what we have. We know that we will need the tree method equals approx. We will need a subsample equals 0.5, I think, and we will need the max depth equals 1. So now we will test alpha, and as you see, we have pretty good score on alpha equals 0.7, so we'll use this alpha. And for gamma, all the scores are looking to be the same, so we will not tune gamma, I think. So the alpha optimum is here, is 0.7. Okay, so now let's just print out those XGB params, which is here. Oops. XGB params. Let's print it. So this is what params we will use to our model, and here is the prediction. As you can see, let's check before. So before all the doing the feature engineering, model tuning and so on, we got the score of 0.85, and here after all of this we got on the same dataset the score of 0. Around 88. Okay, so we improved it pretty good, and what is more important, let's look at our fit before feature engineering 2. As you see here, we have these guys here very low and these guys here very high, and let's look at the fit after it. So we don't have anything very high, any mistakes very high and any mistakes very low. So actually after we doing all that job, we can say that if our outcome, our predicted outcome is above 0.9, we can close to 100% say that the outcome will be 1. And if our prediction is lower than 0.1, we can say that outcome is for mostly 100% it is 0. So that is how we also can use our prediction. Okay, so now we are done. So what we did here, we got the data, analyzed the statistics, looks at the prediction down there. We understood that the data is good enough to analyze, and after that we looked at the error statistics. We understood that we can make prediction a bit better, and we did it by feature engineering and model tuning here. So that's actually all that we can do. Maybe we can make some new features, maybe we can try to grab some new data to make our model better, but from this dataset I don't think we can get some much better predictions. So that's all. Just use FastBenchmark, make data science fun again, and bye bye.